Possibly the worst danger encountered in following seas is the possibility of broaching to. Broaching to occurs once the ship enters the surf riding condition, when it accelerates down the downslope of a wave and loses steerage. Great rotational momentum exposes her broadside to beam seas, and there can be instantaneous capsize. When surf riding, propeller revolutions no longer have a bearing on the ship's forward speed. The researchers identified the surf riding zone, again dependent on ship speed and angle of encounter, and again the safest course of action is to reduce speed. Thus, with both head seas and following seas, the best way to lessen their dangers is to reduce ship speed. Of course, the best solution is to avoid heavy weather wherever possible, and a recent development has been the installation of computer-based heavy weather avoidance systems. These may be particularly beneficial on container ships, where the high stacking can limit visibility of the bow area and could delay the crew's awareness of the forces acting on the ship. These systems warn of potential impact damage and can warn of danger even when the weather looks fine. The input data includes the vessel's speed and direction, wind speed and direction, and wave direction, period, and height, as observed by the watchkeeper or predicted by a forecast. The system computes the highest likely wave the storm will generate, in this case 14 meters. It also assesses the forces which will impact on the bow, largest for head seas, and the encounter wave period. These calculations can be remade for different ship speeds, warning, for instance, if the ship is likely to roll excessively or enter the surf riding condition with the danger of broaching to. Another display, which changes in real time, defines dangerous areas in terms of the ship's speed and heading. The computer calculates longitudinal wind forces which slow the ship and transverse wind forces which cause it to heel. It senses the pitching motion of the ship through a vertical accelerometer in the bow and strain gauges amidships. This is how the ship behaved on meeting a freak wave, a sudden upward acceleration followed by a shuddering downward acceleration. Alarms are built in to tell the bridge of the likely ingress of water or other structural damage. Areas of frequent fog are well documented, particularly in the Admiralty ocean routing charts and other similar publications. The most common type, advection fog, is caused by relatively warm air flowing over cold sea. Knowing that the sea surface temperature usually has a diurnal variation of half a degree or less, there is a reasonable chance of predicting fog by measuring the air temperature and relative humidity and knowing the dew point and wind direction. If relatively saturated warm air is flowing over a cold sea surface, you can calculate when it is likely to reach its dew point and form fog. Once you encounter fog, there are two very important courses of action. Firstly, the ship must proceed at a safe speed, which means slowing down. This is not just to reduce the risk of collision, but because, should there be a collision, the amount of damage is proportional to the square of the impact speed. Halve your speed and you could reduce potential damage by 3/4. In legal proceedings arising from damage claims, the courts have always been highly critical of excessive speed. Secondly, sound the proper signals, but be aware that audible signals often distort in fog, and the direction they come from is not clear. Of course, a very careful radar watch is essential. Again, the usual extent of pack ice and icebergs is well documented month by month, and you must be extra vigilant if ice is likely. In some areas, ice occurs where there is often fog. If the fog is dense, especially at night, the safest course is to stop the ship until it lifts. Radar is not reliable in warning of ice, particularly since up to 90% of an iceberg lies beneath the surface. However, there are useful warning signs. A noticeable reduction of sea and swell and a glassy appearance to the surface might predict pack ice. Providing the ship is not in a known cold current, a sea surface temperature of 1 degree Celsius might warn of an approaching ice edge. And visually, ice blink, a characteristic glare near the horizon, indicates ice. In the North Atlantic, the position of bergs is tracked by the US and Canadian authorities. Should a master see a berg not mentioned in these communications, he has an obligation to report it. Ice which forms on the ship's superstructure will affect weight distribution, and if it forms very rapidly, poses a threat to stability. The conditions giving rise to this are an air temperature of -2 degrees Celsius or less, the ship in heavy seas, strong to gale force winds, freezing rain or snow. In the last 20 years, weather forecasts have become much more accurate and comprehensive. Even so, hazardous weather still presents a danger to shipping, wherever you sail. The number of weather-related incidents and casualties remains unacceptably high, as do the number of incidents involving pollution. With the trend towards totally enclosed bridges, it becomes even harder for the seafarer to experience changes in the weather at first hand. So you need to understand how forecasts are prepared and how to make best use of the technology on board, including computer-based heavy weather avoidance systems if fitted. Only then can you help ensure a safe passage for your ship, your fellow seafarers, passengers and cargo.